Welcome to the deep dive. Today, we're getting into signals, the electrical language that makes so much work.
That's right, it's everywhere.
We've got an introductory chapter to guide us, and, well, the mission is to really get our heads around the two main types, analog and digital.
And also how we, process them, how we actually use that information.
Exactly. It's like figuring out how the continuous real world gets turned into something machines understand.
And then how we can cleverly tweak that digital version to do all sorts of useful stuff.
Okay, so let's kick things off with analog. The chapter says it's basically an electrical mirror of something physical, right? Something that changes smoothly over time.
Yeah, smoothly is the key word. It's continuous. Think of like the volume knob on an old stereo. It sweeps smoothly, no jumps.
Ah, good analogy.
So if you're recording speech, the analog signal voltage tries to perfectly follow the continuous ups and downs of the sound pressure.
And the source shows that simple waveform, like fx changing over x, that really pictures the idea that there's a value at every single instant.
Precisely.
Hmm.
No gaps. And often, these analog signals can be seen as combinations of simpler waves.
Like sine waves. I remember those from school.
Exactly, sine and cosine waves. They go smoothly between -1 and +1. Sine of 0 degrees is 0, sine of 90 hits the peak at +1.
The chapter has those nice graphs showing them. They look, well, wavy.
They are. And you can see how cosine is just like sine, but shifted a bit in time. That's what we call phase.
Okay, phase, got it.
And it's amazing, really. These simple waves are the building blocks. You add them up in different ways to get really complex sounds or images or whatever the signal represents.
So what defines these waves? The chapter talks about properties.
Right. First up is amplitude. That's just the height, basically, the strength of the signal, how high the peaks are, how low the troughs.
It's like turning the volume up or down.
Pretty much, yeah.
Yeah.
Then there's phase. That timing relationship we mentioned are two waves peaking at the same time, whereas one lagging behind.
Okay. Amplitude, phase. What else?
Frequency. Super important. It's how many full wave cycles you get in 1 second. We measure it in hertz or hertz.
The source shows that picture with 3 hertz, 6 hertz, 12 hertz. You can really see more waves crammed into the same second as the frequency goes up.
Exactly. Higher frequency means faster oscillation.
And that relates to wavelength, doesn't
That
it?
does. They're inversely related. Think about it. If the wave is wiggling really fast, high frequency, it doesn't have much time to travel far before it completes a cycle.
So short wavelength.
Right. And if it's oscillating slowly low frequency, each cycle stretches out further in space, longer wavelength. The graphic in the chapter shows that perfectly.
Makes sense. But real-world analog signals aren't always perfect sine waves, are they?
Oh, definitely not. They can be any shape, really, as long as they're continuous and vary over time. They can go positive, negative.
And they can repeat like periodic signals or be totally random looking.
Exactly. The chapter shows a few examples, like a square wave that goes negative and this other kind of messy but repeating signal. It shows a variety.
So where do we actually see these analog signals? The source gives examples.
Loads of places. Audio is a classic one, that Mr. Spock waveform. It's complex, continuous voltage changes, capturing his voice.
The direct electrical copy of the sound.
Yep, and our own bodies. ECG signals track the heart's electrical pulses. Each beat is an analog wave.
And EEGs for brain waves.
Right. You get these different rhythms like beta for concentration, alpha for relaxation, theta, delta, each with its own frequency range and characteristic analog shape. It's fascinating.
Wow. Okay. What else?
Well, seismology measuring earthquakes. The Richter scale is basically measuring the amplitude of those huge continuous seismic waves.
And video. That seems more complicated.
It is, but it's still fundamentally analog in its raw form. You have signals for color, for brightness, for keeping the picture stable, all varying continuously. The diagram breaks it down.
Even it says a grayscale image can be seen as an analog signal.
Yeah, you can think of the gray level at each point as a continuous value. So analog is all about that smooth, unbroken representation.
But it's not always easy to work with directly, especially with computers.
Exactly. Which brings us to the other side of the coin, digital signals.
Right. So the chapter says digital is about converting information into bits, ones and zeros.
Precisely. Before you send it or process it, you turn that continuous analog information into a sequence of discrete numbers, represented by bits.
It's a totally different approach. The source has that great comparison picture, the smooth analog wave versus the blocky stepped digital one.
You see it immediately. The digital signal isn't smooth. It jumps between defined levels at specific points in time. Each level represents a number, like a 1 or a 0, or a combination.
So how do we get from the smooth analog world to this blocky digital one?
That's where ADCs come in, analog to digital converters. And of course, DAC is digital to analog converters to go back the other way.
Okay, ADCs and DECs, the translators.
The chapter has a block diagram that makes it clear. Imagine a microphone picking up your voice that's analog sound.
Continuous air pressure waves.
All right, that goes into an ADC. The ADC measures the voltage of the analog signal at lots of regular intervals really, really fast. It takes snapshots.
Sampling it.
Exactly, sampling. And it converts the value of each sample into a digital number, a string of bits. Now you have digital audio.
Which you can store, edit, send over the internet.
All that good stuff. Then, when you want to hear it, the digital numbers go to a DAC. The DC reconstructs an analog voltage step by step based on those numbers.
And that analog voltage drives the speaker.
And out comes sound again, hopefully sounding like the original voice.
Mm-hmm.
The chapter visualizes this too, showing a sine wave getting turned into those digital steps, each with a binary value.
You can see how it's an approximation, but if you take enough samples quickly enough.
It can be a very, very good approximation. Good enough for high-fidelity audio or sharp images.
Okay, so we've gone digital. Now what? Why did we bother?
Now we get to the power of digital signal processing, or DSP.
DSP, I've heard that term.
So DSP is basically taking those digitized signals, voice, video, temperature, pressure, whatever, using math to manipulate them, usually on specialized chips called digital signal processors.
And why manipulate them?
Well, the big reason, as the source points out, is that real-world signals get messy. When you transmit them or record them, they pick up noise, interference, distortion.
Like static on the radio or a grainy picture?
Exactly. Or echoes on a phone call. DSP gives us the tools to clean that up, to filter out the noise, cancel the echo, and retrieve the information we actually want.
So it's about improving the signal quality.
That's a huge part of it. But DSP does more. The chapter lists several types of processing. Filtering is a big one, isolating specific frequencies.
Like tuning a radio or an audio equalizer boosting the bass.
Perfect examples. Then there's detection, just figuring out if a signal is there. Think radar detecting a plane.
Okay.
Recognition and classification identifying patterns, like software recognizing your face, or medical systems classifying heartbeats as normal or abnormal.
That sounds really advanced.
It is. Then there's coding, which often means compression, making digital files smaller so they're easier to store and send, like MP3s or JPEGs.
Compression is everywhere.
And finally, analysis and modeling using DSP to understand the signal itself, its properties, how it behaves.
Wow. Okay, so DSP is this whole toolkit. Where does it actually get used? The source seemed to have, like, huge lists.
It's almost easier to ask where it isn't used these days. Image processing is massive. Pattern recognition for robots, enhancing medical scans or satellite images, animation, fax machines.
Fax machines still use it, huh?
Well, the principle is there. Then instrumentation and control. Analyzing frequencies in labs, reducing noise in measurements, compressing sensor data, controlling robots or machines very precisely.
What about sound?
Oh, yeah. Speech recognition, talking to your phone or computer, speech synthesis computers talking back, text-to-speech, digital audio recording and effects, equalizers, it's all DSP.
Military applications too, I bet.
Definitely. Secure communications, processing radar and sonar signals to see things far away or underwater, missile guidance.
Yeah.
Very sophisticated stuff.
And just everyday communications, phones, internet.
Absolutely vital. Telecommunications relies heavily on DSP for echo cancellation on calls, making sure data gets through clearly even on noisy lines, video conferencing, mobile phone technology like 4G and 5G.
It's really fundamental.
And biomedical. Patient monitoring systems, watching vital signs, MRI and CT scanners, using DSP to build images from raw data, EEG brain mapping, ECG analysis for heart conditions, enhancing X-rays. It's transformed healthcare.
And then just everything else.
Pretty much. All the consumer electronics, smartphones, digital TV, digital cameras, smart speakers, internet calls. DSP chips are working away inside almost everything.
So wrapping it up then, we have analog signals, the smooth, continuous, real-world stuff.
Right, directly representing physical quantities.
And digital signals, where we convert that into discrete steps, into bits, ones, and zeros.
A numerical representation at specific points in time.
And the bridge between them is the ADC going from analog to digital and the DC going back again.
The essential translators.
But the real power often comes after we go digital, with DSP using math to clean up, analyze, compress, and manipulate those digital signals.
Which, as we've seen, enables a staggering amount of modern technology. It really is everywhere.
Absolutely. It makes you think, With DSP already doing so much, from your phone to advanced medical imaging,
Hmm.
what comes next? What future developments in DSP do you find most exciting or maybe even potentially world-changing?
That's a great question to ponder.
Definitely something for you, the listener, to think about. Where could this technology take us next?